Non, j'aurais dit f de x c'est le filtre, et g de x moins taux c'est le... Parce qu'en fait, c'est-à-dire, en fait, qu'est-ce que le truc de convolution, c'est la convolution au point x, et tu sommes... Disons qu'on appelle ça une fonction, ok, c'est une fonction, et à chaque point x associe c de x, ok. Et là,
un autre point quoi.
Ouais, parce que cette convolution, c'est d'accord, c'est une fonction de x.
Ouais.
C'est pas...
Il y a la fonction, la convolution, c'est la fonction filtrée quoi.
Ouais, ouais. Et que...
הרצאות לראות שזה, אם אני את ההרצאות היום מתשע עד 4 בחוץ, מה את רוצה? זה ממש עוד הרצאות. בשעות הפנאי שלי, אני אראה עוד הרצאות, נראה לך?
זה הסיבה למה לא הלכתי לבריין בי, בוקר טוב.
כאילו בשעות הפנאי שלי אני מספיק על הרצאות ה-EG, נכון? ובואי עוד קצת איש לדבר. שמעתי, לא חייב היום שיהיה לך זמן.
אוקיי.
Ouais, enfin, tu devrais alors t'es coincé, c'est ça. Pourquoi tu bouges que c'est tout? FBS, c'est pas fixe.
Okay, good morning everyone. Put this on and then we start. Not that I really need it, but okay. Here we are. Can you hear me? Okay. So what I plan to do today is basically I try to do this, just go over the major points that I made in the last lesson, so that we are fully that we know where we're standing, and we sort of just a short reminder what are the main points that I wanted to make, and then we will continue. We have to sort of finish the stuff about motion processing. Remember, and I brought this issue of motion processing not because motion processing in itself is an interesting issue, but mainly because it's sort of a classical example of an attempt to compare neuronal sensitivity with behavioral sensitivity. And it raises some very interesting issues that I thought are worth mentioning. So just as sort of as a reminder, if you remember, what we had is the sort of the classical Newsom task in which there's scattered dots that are placed on the receptor field of the cell, and they move either, the degree of the coherence of the dots, that is, what percentage of the dots move in a coherent fashion changes, and that sort of resembles the signal, the level of the signal of stimulus. The more dots moving in coherent fashion, the easier it is to do the task. And then, and if you remember, you can look at, let me just go back, of course. So here's the stimulus and the task. The few points, critical points here is that the monkey must maintain fixation so that the stimulus is all the time on the receptor field of the cell. And then you place the stimulus on the receptor field, and it's on for, 2 seconds or so. And then you measure, first of all, the monkey's performance. Okay, so the higher the correlation or the coherence, usually now we use the term coherence for this, the dot coherence, the better performance is, and you can sort of quantify this by fitting a sigmoid curve, which is sort of the psychometric, and that's called the psychometric function, and assess the threshold. And as I said, okay, we can do the same for the neurons. And how do we do this for the neurons? Well, this is something that's new. So we'll be looking at that neurometric function, which is the equivalent of the psychometric function at the level of a single neuron. And the idea is very simple. First of all, the intuition is clear. You know, the higher the coherence, dot coherence, the less you have an overlap between the firing rate when the stimulus is the preferred direction versus the null direction. And remember, why do we have the scatter, first of all? What's the meaning of the scatter here? So this is the distribution here. What's the meaning of it? Well, you don't remember, but the idea was that, okay, you present the stimulus over and over again, same stimulus, okay? So you may present this on one trial, then you present the null direction, another trial, so on and so forth. But here you sort of accumulate data from the same stimulus presentations, okay? So in all these cases, the white distribution here, the stimulus was at 12.8 coherence in the preferred direction. But there's some distribution here. Because the neuron does not respond at the same level each time you present the stimulus. There's some noise, if you want, an inherent noise in the firing rate of the neuron. Sometimes it fires more, sometimes it fires less. And of course, that is the problem, right? Because there's some inherent noise in the response, you cannot tell if the motion was in the preferred direction or null direction, especially as you lower the coherence. So you see, as you lower the coherence, the degree of overlap between the distribution of the preferred direction responses and the null direction responses becomes more overlapping. So as you move here to lower and lower coherence, the overlap gets to be complete. And if the overlap is complete, if you were to listen to the output of this neuron, you would not be able to tell if it's in the preferred direction, that is with the white bars, or the null direction. But here, you're almost perfect, right? So that's the intuition. We follow this. Is this clear to everyone? Okay. So, and then we said, okay, so this is what I teach in my bachelor's the degree course, third year bachelor degree. So they see this, but we never get into the details of how exactly is this computed. And I want you to understand this. So how exactly is this computed? You have these two distributions, remember? So what you see here on the y-axis is the percent of hits. And what you see here is the percent of false alarms. Remember, so there's two distributions. Should we go over this, or you've heard this? If you know this, I will just step over this very quickly. But if not, it's something I want you to know. I think this is something basic. It's called signal detection theory, okay? And I want you to understand the essence of it and understand how we compute how well is the neuron doing, okay? So the idea is the following. You have, this is the responses, the distribution responses when the movement is the preferred direction, and the black here is for the null direction. Now what we do is we change the criteria. So we start from a criteria up here, and we say, okay, only if the neuron fired, let's say, above 100 spikes per second, will we say that it was in the preferred direction. So what will we get in that case? So if the criterion is here, what will be our chances of hits, which meaning that it was in a preferred direction and we said it was in a preferred direction? Very, very small, right? Because we're using a very, very strict criterion. But what would be our rate of false alarms? Zero. No, zero. Because you never say, what's a false alarm? Saying that the movement was in the preferred direction when it was actually in the null direction. Okay? So here, there's zero. Okay? So you're right here at this point. As you're laxing your criterion, moving from here further and further down, what do you get? More and more hits, right? Because think about it, as you move the criterion, okay, the white bars here, there's more and more white bars that pass your criterion. Meaning that you're increasing your hit rate without getting any false alarms. Okay? At some point, once you get to here, let's say to 50, your criterion is 50 spikes per second, you start getting some false alarms. So initially you're moving here, increasing your hit rate without any false alarms. Okay, so if you look at the sort of curve like this, this is a curve that's drawn as you move your criterion from very high criterion to lower and lower criterion. Is that clear to everyone now? Okay? And initially, you're just getting more and more hits. Okay, maybe I'll write this again. I drew this last time, and maybe it's worthwhile just to draw this again. The two distributions, right? So you have two distributions. Okay, so this is, if it's in the preferred direction, that's in the null direction. And this is, so your x-axis is what? It's the firing rate, right? Spikes per second. And what's your y-axis? It's the sort of the frequency at which you got such and such activity. Okay, so this would be a frequency or a rate. Okay, how many times did you get, say, 100 spikes per second? How many times you got 50, and so on and so forth? Okay, so that's the white one. That's the black distribution there. And so you're moving your criterion. You start with a criterion which is very high, and you're moving your criterion like this. Okay, what do you get initially? As we said, as long as you're below this level here, you're only increasing the hit rate without any cost. As you're moving further and further, you're starting to get a false alarm. Let's just take a specific criterion and understand what do I mean by false alarm. So just you define to me. Let's say your criterion is here. What's your hit rate and what's your false alarm rate? Okay, do you have false alarms? You do, and this is, okay, since I didn't bring any one of you, but this is the false alarm rate, right? That's above your criterion, so you're saying, this was in the preferred direction, while actually it was in another direction. Okay, everyone follows me? Okay, good. So this is a way to quantify performance at the neuronal level. And so what you get is typically this sort of what's called an ROC curve, receiver operating curve, which looks like that. And then what do? You integrate over this one, okay? So if there's no information whatsoever at in the cell's firing, what do you expect? The two distributions, what should be with them? The two distributions that I was just talking about. I want to hear you, okay? It's important that you understand this, okay? So what happens to the two distributions? You can look here. I mean, what happens if there's no information? They should be overlapped, completely overlapped. So as you move here, you're changing the level of hits, but you're also changing at the same rate the level of false alarms. So you're increasing both of them at the same time, okay? And then what you're going to get in this graph here, how's it going to look? Along the main diagonal. So if you integrate here, so this goes between 0 and 1. If you integrate here, what are you going to get? A half, which is chance performance, right? There's two alternatives here. That's chance performance, okay? Now, if performance is perfect, how should it look like? Yeah, a step function, exactly, right? Going up all the way to 1 and then staying here, right? Because they're non-overlapping, completely non-overlapping. So you can find a criterion, it's almost the case here, you can find a criterion where you get all the, you adopt a criterion where all the y distribution is above your criterion, okay? But all the dark ones are below your criterion, okay? So that would be ideal. And then, so you get these distributions for each level of coherence, and then what you do is just integrate the area under the graph. So if you integrate the area under the graph, if it's along the main diagonal, you're going to get 0.5, and if it's jumping like that, you're going to get a value of 1. So these are the bounds, okay? And that sort of leads you to what's doing here. So that's the neurometric function. That's how you compute it, you know, from the integral of each of these lines. The blue lines for a very low coherence. As you move here, it's higher and higher coherence. So the integral is closer to 1. And this is how you quantify the neuron's performance. Okay? So we talked about this. I took some time to go over this again, because it's essential that you understand this. And then moving to what we found, well, the surprising thing was, and I'll move here, was that the neurons, the average neuron was almost as good as a monkey, right? Which sounds ridiculous, right? Because using many, many neurons to, presumably using millions of neurons to do the task. So how can it be, okay? And the other finding was, remember that I talked about here, was that sensitivity, if you were to look at cases where actually there's no net motion, or no net motion on the screen, because the dots move, each one moves in its own direction. So if you look at the percent of coherent dots moving in a specific direction, it's 0. It's just random motion completely. You still find, that's another application of this analysis, you still find that in some cases, or it's actually in many neurons, the activity is higher when the monkey makes a decision in the preferred direction rather than the null direction. Okay? So it reflects the decision of the monkey, not what happens on the screen, because on the screen it's just random motion. But the monkey has to make a decision. Is it in the preferred direction or null direction? So it does. Okay? So it does, and you find that when the monkey makes a decision in the preferred direction, although the stimulus is the same, activity is higher. Right? Remember this? That's also surprising. Why? Because it suggests that the single neuron has an influence on the decision of the monkey, right? Because the individual fluctuations at the level of a single neuron seem to affect the monkey's behavior. And if there were millions of neurons doing the task, then it seems that you shouldn't see that the individual fluctuations of the individual neuron should reflect the monkey's decision. Okay, so this is what I brought up last time, and then I had an answer to this, or at least a good partial answer to this. Remember what it is? You don't. It's all completely okay. Tabula rasa. Okay. It's a new day. It's early. I understand. Okay. So, no, Diana, you know this because she's teaching this. So she's the TA. Okay, in my course. So, okay, what is the answer? Right. So, one way to understand this is, okay, this is all true that if you had 1 million neurons, if the activity of individual neurons, pairwise neurons, is uncorrelated, then surely, yes, you should get better, okay, because you can reduce this noise by averaging across greater and greater populations of neurons, okay? But that's if they're uncorrelated. Once they're correlated, it's a different ballgame, okay? And you can show that, okay, these neurons are correlated to a very small extent. You know, the correlation coefficient typically is 0.1 or something like that. You'd think, okay, that's very close to 0, which is uncorrelated. But if you do the math, you can show via very simple analytical solution from the math that you'd expect that the signal to noise of the pooled response, not the one neuron, should asymptote very quickly, even if the correlation is very, very low. So that was part of the story, was that, okay, decision is based on the comparison between pools of neurons, those sort of signaling an up signal and the others down signal, and you compare the two, well, that should sort of asymptote very, very quickly. So if you notice, if there was no correlation between the neurons, you should expect this to grow as a function of square root of n, okay? That the signal to noise should grow as a square root of n, as is the case in the central limit theorem and statistics. Well, that's not the case if the correlation is very, very, even if the correlation is very, very weak. And the signal to noise should improve by a factor of 2 or 3, but not more than that. So in that case, 1 million neurons is only 2 times better or 3 times better than 1 neuron. Okay? So that's a major, major difference. The other thing that I mentioned last time was that it's not only that, but you can also, if there's a correlation between the individual neurons, you can also understand why the individual neuron has an effect on decision. And the idea was, okay, they're all correlated. Think about them, just to sort of put this in artistic way, think about them fluctuating. What does it mean that they're correlated? They're fluctuating together, okay? So if they're fluctuating together, okay, if one neuron says, this is in the, sort of, in its firing rate is pointing that it's in the preferred direction, the other neuron also tends to be doing the same thing, okay? So in that case, as you're increasing the number of neurons, the relationship between the neuron, the individual neuron, and the pooled response, which means the population, not just the one neuron, you should expect this to decrease, okay, as you're increasing the number of neurons that play in the game. And if the correlation between them were 0, it should drop basically to 0, okay? The one neuron would not have any effect on the pooled response, a very marginal effect on the pooled response. But if they're correlated even to a very limited way, so R is 0.1, you can see these lines here, which correspond to the fact that, okay, you'd expect to still see a correlation between the individual neuron and the pooled response. And since we assume that the decision is made on the basis of the pooled response, you should still see that can explain this result, which is to start with, a very, very puzzling result, that the individual neuron is a predictor of what the monkey will do, not just what is the stimulus on the screen, but what the monkey will act when the stimulus itself is just completely random. Okay? So this was where basically we ended last time. I hope it's clear. If it's not, I mean, these are sort of essential points. I want you to understand them. They're sort of, I didn't get into the full math, but I tried to convey the intuition and to make sure that you understand the essentials here. I wasn't sure that that was the case last time, and I make it a point to come back and reiterate things. So can I move? If there's any questions here, I'll move on. Okay, so the next step is following this was, okay, great. But we think the decision is based not on one neuron, not on 10 neurons, but on multitudes of neurons. We do not exactly know how much, but probably of the order of, hundreds of thousands to millions, okay? So, can we, I think till now, the point is that till now what we've shown you was that, okay, the individual neurons are almost as good as the average monkey, okay? What we haven't showed you was the element of causality. What we want to make the point is that you can change the monkey's behavior by somehow intervening with the neuronal activity at a given area, okay? So these are the early days in the 90s, which I'm telling you. I'm sure you're going to hear, if you haven't heard yet, you're going to hear all about optogenetics, okay, in which it's sort of this technique has now been applied in a different way. We'll talk about this in a few words, using optogenetics, but the core is here. And so I wanted you to know basically the history, just so that you have a perspective on things, okay? So the idea was, okay, let's not just record from individual neurons, but let's try to stimulate, okay? And not individual neurons, because we don't think that the decision is based on individual neurons, okay? How are we sure about this? Well, from time to time, as you move the electrode, you kill one neuron or two, just as you penetrate to it, and then, firing stops after a while. It gives a big burst of spikes, and then, after a few minutes, it dies out, okay? The monkey doesn't change its behavior. Right? And it's clear that, that the behavior is not based on any one neuron or any tens of neurons, okay? Now, so what you want to do is try to stimulate a population of neurons and affect the monkey's behavior. That is the idea. So when is it going to be, how are you going to do this? Well, at the time that I'm describing to you, they didn't have optogenetic tools, so you couldn't stimulate a specific population of neurons. Okay, let's say pyramidal cells at a specific layer 5 pyramidal cells as they do today, or something like that. So what you could do is just move the electrode and stimulate electrically, not using light as they do now, but electrically stimulate the cells which are in the vicinity of the electrode. Okay, so that is the idea. And, okay, do you expect to get any effect? Let's say, okay, so now you have your sort of, you have the electrode, you move your electrode. What is the sort of required criterion for this to work? I would say that the required criterion, first of all, it's unclear. When they started this, when Bill Newsom started this work, it was unclear at all that you're going to be able to affect a monkey's behavior. That is the target here, to affect the monkey's behavior by stimulating the cells. But a prerequisite for this is that the cells, the neurons that you're going to stimulate, are going to be somehow doing the same thing, right? Think about you want to affect the monkey so he'll see motion, let's say, upwards. Well, you want to target neurons that are upward encoding neurons, okay? And the idea is, okay, now, if you're going to selectively activate upward encoding neurons, well, now when the monkey has to discriminate between upward and downward and you're activating them, you may bias his decision towards the upward motion, okay? So the point is that you need to have some homogeneity. You have to have not just to stimulate all neurons, but the ones which are selective for some direction of motion. The good thing about they were somewhat, I mean, it wasn't just luck, but the thought that we knew that in MT, okay, MT is this area in the monkey cortex is organized somewhat similar to V1 in columns, okay? But the columns, we talked about columns in V1, we said they're orientation columns. Well, in MT, it's not orientation columns, but direction columns, okay? So how do you see this? Well, this is an individual penetration done through, you see, this is layer 1, this is layer 6 of cortex. So you're moving here, penetration is almost normal to cortex. And what you can see is that, okay, and each dot here represents the preferred direction of one neuron. So this was the first one, second one, so on. And so x-axis is the track distance, and the y-axis is the preferred direction of that neuron. And what I want you to notice is that they're, nearby neurons have similar preferred directions, okay? Now, of course, there is some change here, and that's because the penetration is not normal to the cortex, but at some angle to the cortex, okay? Okay? So, but it's not random. I mean, if nearby neurons did not have the same preferred direction, you'd expect the dots to be, jumping. This one would be here, the next one would be here, the third one would be here. Should be just random, okay? Just a random cloud. But it's not so, okay? So nearby neurons have similar preferred direction. Okay, so that's an opening, an opening that allows you to think about the following experiment, okay? So the idea is the following. Okay, so here's your piece of cortex from layer 1 to layer 6 here, and you're moving your electrode, and you record from the same one neuron. What do you see? You see it's the preferred direction. Let's say its preferred direction is this one. You're moving to the next one, next, it's here. You're moving to the next one, it'll be something like that. There's some scatter in the preferred direction, okay, but that would change, and at some point it may change to, sort of as you move here, so the preferred direction may change somewhat if you're not completely normal to the axis of the layers in the cortex. But then what you do, okay, so you map this across the electrode track. So the points here correspond to where the electrode here. It's first here, then here, then here, and so on and so forth. You find where you have a cluster of neurons that have the same preferred direction. And so let's say here, the preferred direction doesn't change much. Let's place the electrode right here and stimulate the neurons, so now you're passing a current through the electrode, and you're stimulating, depolarizing the cells, bypassing this current through the electrode, okay? So what you get is, okay, if you increase the current, you're going to recruit more and more neurons. So you want to sort of stay in a current where you're going to recruit many neurons, but generally stay within the bounds that you're stimulating a homogeneous population of neurons. Okay? So that's the idea. And now what you do? Well, now you do the following. So you do a slightly different experiment than what I told you till now. Instead of doing just recording, you're doing a micro-stimulation experiment in which you, again, so the monkey is fixating, it sees motion either in the preferred or the null direction. Where do you place the stimulus now? It's a question to you. Okay, so now we're not interested. Why am I answering so quickly? Okay, think about it. Okay, so where do you place the stimulus?
The layer. We have the direction for each layer, right?
Where do you place the stimulus on the screen? No, okay, we know where you place the electrode. You place the electrode at the optimal position.
Find the receptive field.
Okay, right. So, but now you have to look at not just the cells, one cell's receptive field, but a population receptive field, okay? So one neuron's receptive field may be here, the other here, so on and so forth. So you can now, you sort of generate put it this way, you place the stimulus at the population receptive field. So it's a little bigger than the receptive field of each of the individual ones, but it's sort of the grand average of these, of the neurons you want to stimulate, okay? Good. Now, how do you set the direction of motion? According to the preferred direction of these neurons that you are have been recording from, okay? Now, another point to notice here is, okay, you've been moving your electrode, but you know the receptive field of neurons and their preferred direction only along the electrode track. You don't know, okay, so this is in one dimension, you're moving your electrode forward and you record the cells as they are, but you don't know what happens with the other cells. What about the cell which is here? What about a cell which is here? What about a cell which is in the Z dimension? Okay, so you may be wrong. I mean, it could be that, okay, it doesn't assure you success in the sense that you're going to stimulate a homogeneous population of neurons, but it's the best you could at the time. That was the techniques that they've had. Okay, so we described this well, I think, and now, so you place the stimulus at the population receptive field, okay, the average receptive field of all the neurons that you've recorded, and now you start the experiment, and now what's added to what was before is this, the visual stimulus appears. The monkey still has to maintain fixation here, right? Because otherwise, if it, I mean, it has a tendency to move its fixation to here, but then the receptive field will move, right? So the monkey is trained to maintain fixation here, and you have eye tracking to make sure that that's the case. And then you present the visual stimulus, but what is added is also an electrical stimulus, okay? So at the time that the stimulus is presented on the screen, simultaneously there's an electrical stimulus which drives the cells, okay? It activates the cells, okay? So now what do we have? We have an interaction, or we have two components here, the visual stimulus and the electrical stimulus which drives the cell, the cells, okay? So what do you expect? Yes?
The electrical stimulus, is it just one stimulus across all the cells, or is it for each cell?
Okay, so when I'm saying electrical stimulus, I didn't mention, the electrical stimulus, first of all, is a train of pulses, okay? So it's typically something which looks like this. Okay, here's one pulse, biphasic, two pulse. Not all the layers, because you're in one specific layer, but it's for all the cells in the vicinity, no, not in that layer, in the vicinity of the electrode, okay? Okay? And this could be, so you have here, and there's a timing between one pulse and the other, so it could be 20 hertz, it could be 50 hertz. Usually that's, typically used in 100 or 200 hertz just so you'll get a vigorous response from the cells. Okay, but I want to get back to, sorry, I just noticed. That's better. Okay. No, the stimulus moves on each trial. It moves either in the preferred or the null direction. And the monkey has to make a decision. Is it preferred or null? Okay? And if it answers correctly, it gets juice. That's the name of the game. So the monkey is motivated to identify, categorize the stimulus correctly. Okay? Okay, so what do we see? Okay, so now we have an interaction of the visual stimulus and the electrical stimulus, right? Now, what can we see? We can see that basically, here's the graphs that you get. So here's one experiment. Let's focus on this one. That's another experiment. What do we see here? Now the x-axis is the correlation, meaning dot correlation. So positive values means that dots move in the preferred direction. Negative values mean that the dots moved in a null direction, okay? Now, the y-axis is the proportion of preferred directions. So notice it's different from what I mentioned before. It's not proportion of correct answers, but rather it's the proportion of preferred directions made by the monkey, okay? So what do we see here? We see a graph that shows, let's look first of all at the white dots. That's without microstimulation, that's with microstimulation. So let's make the point when, what do we see first of all? That there's a shift of this curve to the left, okay? And let's take just for, to explain it better, let's look at the zero correlation. That means dots are moving completely random, okay? When you're not stimulating the neurons through your electrode, you get that the monkey says that the chances for the preferred direction are very small. However, when you're stimulating, although the stimulus on the screen is just random, when you're stimulating, you get this jump, okay? And this is true. So look at the amount of the jump. It's quite dramatic here, right? Okay? That is the effect of your microstimulation. Another way to actually, what is typically characterized is the jump along the x-axis, so the shift leftward, because you can say that this shift is equivalent to what is the effect of the visual stimulus. So that's two ways of looking at it, which are basically are very similar. But I want to make a few points here. Okay? So first of all, you get an effect of the microstimulation, and the effect should be in what direction?
In the preferred direction.
Exactly. I mean, we have a very clear prediction that it should be in the preferred direction, not in the null direction, right? Okay. So you see these are 4 different experiments. You see that it's always a shift leftward, meaning that there's a shift towards the preferred direction. Okay. So we are biasing the monkey's behavior in the predicted way. Okay. Now, okay. Another question for you guys: Why is the effect here much smaller than the effect here?
Or Q from other neurons? No, Q from other neurons. Like if there is some correlation, so the pool infers in some way, and so the information of that neuron is quite.
Well, wait. It's not an information from a neuron. No, it's an information from a population of cells. Okay, we're not talking about one neuron here. I mean, the whole effect here is done through many neurons. Okay, you're stimulating a great population of neurons. Maybe we have the assessment is of the order of hundreds of thousands. Okay, so I stopped you there. It's not a neuron. Okay, just make that clear. But again, okay, so I stopped you.
Populations that also answer the stimulus, and so you can also use them because you have like a Q.
Okay.
On the screen.
Okay. So the point is the following. I think you're absolutely right. Let's just clarify this. When using it, I mean, think about this. We have 2 effects here. One is an effect caused by the visual stimulus, and another is an effect caused by an electrical stimulus. Okay? So, and they interact, right? So if you are presenting, say, a stimulus at 20% coherence, okay, then the cells which are sensitive to motion in the say, leftward movement, which is the preferred direction here, are firing, okay? On top of that, you're activating them through the electrical stimulus, okay? So you're getting a slight increase in the proportion of preferred directions, but not much. Because if the visual stimulus is so dominant, let's take a case where the visual stimulus is 100% coherent. Well, the visual stimulus is completely dominant, okay? So the electrical stimulus would not add much to it, okay? When would it add the most? When the visual stimulus is completely random, right? So you expect, it's no surprise that the greatest effect is when the visual stimulus is just completely random, okay? And then the electrical stimulus can have its greatest effect. Okay. Now let's understand so now that we understand that, yes? In the? Okay, so these are different experiments, okay? So again, okay, if you look here. B? D. Sorry, yeah. Okay, so in D, you're right that here it seems that this is not much different than this, right? That's what you're pointing out to. Okay, the problem is here that you don't quite characterize all the range of psychometric curve, okay? If you were to extend the coherence, okay, to minus 100 and 100, you would see that this drops down, okay? And it would look exactly like that. So it's only an issue. Do you follow the logic here? So it's only an issue that in this case, your choice of parameter was not ideal in the sense that you never get to 0 proportion preferred direction here. And you stay within a very small bound, okay? So it's not ideal in that respect. But I argue that if you were to expand the coherence levels, you'd see something similar to this. And I want to get back to this and understand this just to make sure. Okay, so one other question here. What would be the ideal performance? What do you expect the ideal performance to be like? So notice here, this is I'm emphasizing this again. It's preferred direction. It's not correct answers. How would you expect performance to be if you would, exactly, you should see a step function, right? So the negative values mean that the motion is in the null direction, positive ones, motion in the preferred direction, right? So ideal performance would have been a step function at 0, right? Okay, so you see that, you know, the higher the coherence, okay, the closer you are to the actual expected values, perfect performance. And as you're moving to the range where the coherence is 0, okay, you deviate from this sort of step function, and you see a sigmoidal curve because it's much more noisy in that domain. So, okay, I think we've delved quite a bit on this. And just to end this, because I want to get, okay, go ahead.
I'm just not sure why you see it like this. On the 0, it's mostly in all directions.
You mean here?
No, in the 0 correlation.
In the 0 correlation?
Some will prefer in all directions.
Okay. Okay, that's a good point. Let's think together. I mean, you'd say, okay, at the 0 coherence, what do you expect? That I'll say, there's no information from the stimulus, so I'll just throw a coin and say up or down, right? Okay, so I should say 50% of the chances I'll say up and 50 down. And here in the non-stimulated trials, which are in the white ones, you see that, okay, your choice is much smaller, okay? How do you understand this? Because you're sort of compensating for what happens. Half the trials are stimulated trials, and half the trials are non-stimulated trials. The monkey doesn't know which one is which, okay? All he knows, okay, there's a trial, there's nothing on the screen, it's just random motion, I have to pick up my to make a choice. So because microstimulation affects the trials on micro-stimulated trials, and you tend to choose the preferred direction more often than 50%, okay? See here that this is greater than 50%. Then there's sort of a compensation. So if you take the grand average of this point and this point, it's going to be around 50%. That's the idea. Okay? Another question there? Oh.
Actually, I had exactly the same.
Good. It's a good point. I mean, I sort of I jumped to sort of speed up, but it's good to understand everything here. So the point here, first of all, is that's just the sort of average result from all experiments. And what you can see is, that almost in all cases, there's a shift leftward of the function with microstimulation, meaning that the microstimulation effect is in the direction that we expected, okay? And that's shown here. That's a sub-case of the experiment. So the y-axis here is the number of experiments, and the x-axis here is the equivalent visual stimulus. And if it's positive, it means that there was a shift leftward of the function as we expect. And you see that the grand majority of experiments are shifted to the left, meaning that there's a positive value here. And notice that in some cases, it's really great. I mean, think about it, that you get an effect of, 40% coherent dots. So just think of it. I mean, just to experience this is amazing in the sense that here you are. You see the monkey performing the task. And there's microstimulation, but the stimulus is clearly moving in the null direction, and he points to the preferred direction due to the microstimulation. Now, of course, your brain is not microstimulation. You can see that it's going in the null direction, but the monkey doesn't know on what trial, what is happening in each trial, so he's just basing his decision on the population of neurons, and therefore, you see this effect. So it's a very compelling effect, and what do we get from this? We get from this one important and key aspect, and that is causality, okay? You've affected a population of neurons, and you can show that you have an expected result as you predicted, okay? That there's going to be a shift towards more decisions in the preferred direction. So I think it was, this was like back in the 90s, but it was a very, very compelling result, and, a classic that I wanted you to know about. Okay, now there's just a few points to mention. First, what happens if you, it's very sensitive to where you place your electrode. Why is it sensitive to where you place your electrode? Because if you move your electrode a bit, let's say, so instead of placing your electrode here, you move it further on. Well, now, as you're stimulating, you're not stimulating a homogeneous population of neurons. Some of them have a different preferred direction. Then you expect that your effect is going to decay very, very quickly, right? So it's crucial that you do your best to stimulate a homogeneous population of neurons. And that's shown here. What you see here is the effect of the microstimulation. So the higher here is a greater effect as a function of where you place your electrode. So as you move your electrode, I don't know, another 100 microns, you get a much smaller effect. So here, in this case, in this experiment, the effect was, I don't know, 40%. If it were in one position, if you moved it further away, it dropped almost to 5% or something coherence. So very, very small effect. Okay, so it's very dependent. And here's another experiment showing the same thing. So it's very dependent on that. It's also very interesting to point out that it's specific to where the stimulus is. Okay, so here's two experiments that you can do. One is, okay, you have your fixation, and you place the stimulus at the receptive field of the neurons. And remember, it's not it's a population receptive field of the neurons that you've been sort of recording from. In another, you place it in a different position. Okay, so now, what happens in this case when you place it in a different position? That's shown here. Okay, so here, what you see here is the effect. Okay, again, this is the proportion of preferred directions as a function of the coherence. Positive is in the preferred direction, negative in another direction. And basically, if you see, you look here, you see that the black dots and the white dots just overlap. So there's no effect on microstimulation. You place it in the receptive field, you get a great effect. You place it outside the receptive field, you get no effect. What does that mean? Well, think about it. What is if you place it outside the receptive field? Okay? Okay, so that's my last point before we take a break. The idea is the following. Think about that. You have to assess, as far as the monkey is concerned, you have to assess motion here. Okay? There's a population of cells which is sensitive to motion here. Okay? Now there's another population of cells, somewhat nearby, which are sensitive to a different position. Okay? Say here. Now the monkey knows that what's important for him is to decide what's happening in motion here. Okay? So let's think that you have to decide what's happening here, and suddenly I do something there. Well, you can easily ignore this. This is irrelevant because you base the decision on what's going on here. Okay? So what we have here is basically the following. The electrical stimulus activates a different population of cells, right, that maps something in an area, okay, which is irrelevant now for decision. Decision is based on what you see on the screen. Okay? So you see something on the screen, you have to decide if it's going upwards or downwards. That means that we have to take a break, I guess. Okay? So basically you see here that this is spatially localized. The effects of microstimulation are spatially localized. If the stimulus is placed outside the receptive field of the neurons, you ignore it. Okay? So in order to get an effect, it should be spatially localized. Okay? And one last point. I know I'm running over time. We'll take a break. I just want to finish this. Is a few things. What happens if you're now increasing the rate at which you're stimulating? What do you expect to have? So you're stimulating the neurons, and now instead of stimulating them, I don't know, 20 times per second, now you're stimulating them at 200 times per second. The effect should be magnified because basically the neurons follow your stimulation protocol. Okay, so for every pulse you get a spike, basically. Okay, or on average. Okay, so and indeed that's what you see. You see that when you increase the frequency, the psychometric curves sort of move leftward, meaning that you get greater and greater effect. Okay, and you can see here that's the average. So these are two experiments. You see this shift to the left with frequency, and you get an increase in the effect of the microstimulation. Okay, last question. What if you now, instead of changing the frequency, you change the amplitude? Now, before I show this, okay? Any idea? Right, so as you increase the amplitude, you're recruiting more and more neurons. Okay, you can think about it as a volume of current that is increasing as you're increasing the amplitude. Okay? At some point, so initially what do you expect to get? You recruit more and more neurons that have the same preferred direction, right? Okay, because there's a column, so there's a sort of basically the columns are organized so that within a restricted space, all neurons have, or the majority of neurons have the same preferred direction with some jitter, okay? As you're but at some point, you're going to move to a different column, okay? And then you're going to abolish your effects. And often, not only that, but the columns have opposite direction, preferred directions. And then you're just going to introduce new noise, okay? So that's exactly what you see. You see here that, okay, now you're changing the amplitude. So initially, you see that the psychometric curves shift to the left, but at some point, they get flattened. So look here, you know, if you're using 80 microamps, you're messing up the monkey's behavior altogether. So initially, you're introducing more signal, leading to a greater effect of the microstimulation, but at some point, you reach noise. Okay, and we'll take a break, and we'll continue with this. We have some stuff after the break, so let's take a 10-minute break and get back here at 10. And I'll try to end earlier than that because I want to have a sort of some time to have a sort of an intro for what we're going to hear from the students on Sunday. Let's take a break now.
Calcul au point X, fonction variation. C'est intègre chez produit. Quand on apprend sur tu apprends tous les L qui sont avant. Après, donc à un moment, positif, à un autre moment, il va être négatif. Donc quand tu choisis X, tu vas faire varier les L. Bon, tu veux calculer la fonction en un point X. Là, on intègre sur tous les L. Tu vas voir chaque point. Soit tu m'écoutes, soit tu m'écoutes pas. Non, mais je... Alors attends, écoute-moi. Tu vas calculer la convolution en un point. On va faire chaque X. Ça va te donner une fonction de θ à la fin. D'accord? La fonction de convolution, c'est la fonction de θ. Là, on calcule. Là, on calcule un en point X. La valeur f. Tu fais varier ces f de moins l'infini à plus l'infini. Qu'est-ce que ça veut dire? Ça veut dire qu'au début, donc d'abord X en L, on va être positif,
partie d'abord par ta fonction. Cette partie que tu filtres, ouais, par la fonction. Pour toutes les parties qui sont alphabétiques, tu vas les utiliser cette partie-là. Et donc, donc en enfant, tu vas avoir un système organique. Ça va de capter à quel point ce motif est présent dans ta tête. Tu vois. Parce que, imaginons, là, à ce moment-là, c'est positif. Tu fais varier les N de moins jusqu'à 10. Les autres, tout le reste est négatif. Donc, tout le reste est positif. Tu prends tous les S, plus petit que 8. Et tu prends tous les S, plus petit que 8. Tout le reste est positif. Tu prends tous les S, plus petit que 8. Tu vas multiplier. Là, tu vas faire du 0, du 0 fois le S, 0, 0, 0, comme ça. À ce moment-là, tu vas voir, là, les limites c'est 1 fois l'expo, ça marche par l'expo. Et après 0, 0, 0. Non, ça c'était juste pour achever ça. Non, mais l'idée de faire bouger, c'est pas... Non, on fait pas bouger. C'est-à-dire, parce que toi, ton idée, si tu fais bouger le filtre, quand tu fais varier les points, à X degrés, il ne bouge pas le filtre.
Ok, alors disons, tu mets un endroit précis le filtre, donc c'est partout en fait 0, et tout ça, ça va devenir...
Imaginons là, tu vas avoir la valeur X. Tous les S plus petits que X, tu vas avoir 0 fois la fonction, 0 fois la fonction, 0 fois la fonction, 0 fois la fonction, une fois la fonction, une fois la fonction, une fois la fonction. Après, tu passes S plus grand que X une fois. C'est juste, je suis d'accord que ça aide pas.
Tu veux dire quand X transforme en FR.
Ouais.
Ça va transformer en FR.
Je sais pas pourquoi je trouve ça plus clair de séparer.
On dit que c'est plus petit que la valeur absolue de S. Voilà. Tu vois ce point ici, c'est quoi?
Ça c'est 0 U égale 0, U c'est 0. Donc ça c'est ta valeur de X. C'est là que je suis.
Ouais, non. En gros, tu prends un point, et là où il y a le carré, tu fais ta multiplication.
Imaginons on a écrit 1, tu vas capter juste ça, tu vois. Tu vas faire 0 fois ça, 0 fois ça, 0 fois ça. Et donc en fait, l'intégrale, qu'est-ce que ça va être en fait? Ça va être l'intégrale sous cette forme-là. T'intègres ce qu'il y a là, ce qu'il y a là. Maintenant, tu peux calculer en un point x'. Bon, c'est contenu, hein, mais c'est bien contenu. Tu veux calculer en un point x'. Tu vas faire le même truc, sauf que tu vas regarder en x. Et donc ça va capter comme ça. Tu vas calculer l'intégrale sous cette forme. C'est un x'. C'est clair ou c'est pas clair? Et quand on dit, tu vois, et c'est là que genre, en fait, on dit Zoharé, il explique les mathématiques de manière intuitive, et c'est là qu'il rentre dans les détails, c'est qu'il te dit, ok, tu fais bouger ton point, tu vois, tu fais bouger, tu prélèves le truc, mais tu vois pas concrètement par rapport au mètre. Voilà, et là, tu vois, en fait, en un point X, tu bouges pas. Quand tu fais varier par rapport à X, tu regardes dans chaque point X la composition, tu vois que ça va être l'intégrale. En fait, en chacun des points X, tu vas prendre une intégrale pensée en X comme ça, de longueur z, enfin non, de longueur ça quoi, de longueur z, et tu vas prélever cette intégrale. Tu vas prélever l'intégrale. Donc je veux dire...
En fait, je crois que je comprends ce que tu veux dire. Mais ça va être différent de 0 que quand
Ouais, ok. Non, on va juste là. Ton axe cognitif, et le dérive cognitif, c'est là, il est réglé. Ce que je veux dire, c'était juste pour montrer que tu balayes tous les stades.
Non, en gros, que tu fais la multiplication des deux fonctions pour tous les stades, pour toutes les valeurs de S. Et après, tu as un point central, après tu bouges ton x.
Et après, comme tu le fais de manière continue, donc là, en fait, ça, d'une certaine manière, ça va te permettre de prélever l'air sous cette forme. D'accord?
Ah oui, c'est bon, pour ça, je prends l'intégrale de ça.
Tu prends l'intégrale. Imaginons que ça, c'est vraiment 1. Ça va te donner vraiment l'intégrale de 1. Et en faisant bouger, en calculant sur de manière continue, tu vas prendre à chaque fois progressivement les intégrales. Et c'est là que tu de ça à...
Et ça te ferait avoir un... Ça, c'est un high pass filter, non?
Non.
Non, quand tu as un truc...
High pass filter, c'est-à-dire que ça laisse passer que les hautes fréquences. High pass, ça veut dire que imagine, high pass filter, ça veut dire, imaginons que tu as un truc comme ça. T'as une composante de grosse fréquence, ok, et des composantes de manière plus générale, et basse fréquence.
Et là, plus ça.
C'est ça.
Et ça, ça, tu fais pas ça?
Sur quoi tu ferais ça?
Non, en gros, ça dépend de l'instance de ce pic.
Ça dépend de... Disons que plus il sera grand, plus il sera petit en tout cas, plus tu vas capter les petites intégrales. Ça dépend de...
Oui, plus il est petit, plus ça laisse passer les grandes fréquences.
ליני הנעים. לכן כפו שם לסגור קצת, כאילו קצת מוגזם. Okay, have a seat please, and we'll continue. So I think I gave you the basics at what happens at empty, okay, this area in which the vast majority of cells are direction selective, and you can and they're organized in these clusters or columns so that you can utilize microstimulation to get an effect which is predicted, okay? So, and therefore you're establishing causality. But MT is not the end of the road, okay? And there's another area called LIP, and a lateral intraparietal sulcus, so and for short LIP, in which we think, okay, remember the monkey's behavior consists of understanding what the stimulus is and planning a decision, and the decision is in terms of an eye movement, either to signaling the motion was in the preferred direction or in the null direction. So remember, okay, so here's your fixation. The fixation is on, and then there's these two lights which sort of represent to the monkey the possible movements that he can make either in one direction or the other direction. Okay, he sees the movement on the screen, and if let's say movement is leftward, he has to make an eye movement to the left target. Okay, and so now we're talking about an area which is involved, as we'll see in a minute, in the motor aspects of making the saccades, the eye movements, okay? And typically what you find in LIP is that it has what we call the motion field, okay, or a motor field in the sense of that it would fire higher when the monkey is about to make a movement to the left target than to the right target, okay? So it's sort of a motor related, since it's encoding the action. Generally, the firing starts before the saccade starts, so there's an element of planning what sort of action will you make, okay? And we'll get into that in a minute, But what I want to talk about now is elements that have to do with perceptual learning. What do I mean by perceptual learning? The fact that, okay, if you repeat this task over and over again, okay, typically the monkeys as well as we get better. Okay, so initially our threshold would be at around, I don't know, 20% coherence. With practice, it may go down to 10% coherent or 7% or 5% coherence. Okay, so we improve with time. And basically, you can see this here. What you see basically is, so you look at session number 11, and you see this is behavior here. So the gray level here corresponds to the percent of the coherence of the motion. Okay, so this is for easy, 100% motion, and gray dots here are for, I don't know, 0 or 3.2% coherence. And what you see here, the x-axis is time. So how long was the stimulus on, and what was your performance? So you see, okay, if it's higher coherence, it's easier to do. Okay, if it's low coherence, you're doing poorer, and you're not gaining much here. Basically, there's some gain with the time that the stimulus is on. Okay, so I see you're freezing. I'll go and close it. Okay. Sorry. Okay, so what we see here, compare this to this. Okay, so what you see that in later stages, in session 142, you get better. And you get better in the sense that, if it's sort of medium coherence levels, your percent correct is higher than here. And you can see this, another way to look at it is here is to say, okay, as a function of time, how much time the stimulus was on the screen, how does your threshold drop as a function of time? So if the time is longer, you can integrate information over longer periods, and therefore you expect that the coherence, that the threshold in terms of coherence level would drop, right? So you see this here, and you see that in the late stage, it's much more dramatic, and compare this, the dots here to here, you see that there's big effect, okay? So you get better, okay? And that's just to show it in another way. So you see here the threshold in terms of coherence for one monkey and the other monkey, and you see that, with the sessions, they get better, okay? The red graph is the error rate. So initially, they may make mistakes at 100% coherence, meaning that they don't quite understand the task, but that asymptotes to basically 0, right? So they fully understand the task if you present a fully coherent stimulus, okay? So the point to notice is that there's a clear improvement in performance. And the question that was asked was, okay, there's an improvement in performance. Well, if there's an improvement in performance, what can account for this? Okay, so one way to understand this is that you get better, that the empty cells, which encode the motion, are getting more sensitive. That's an option, right? Now, what you find is, okay, so here, it's tricky. Again, this is like 10 years ago, and this is the techniques that are in the monkey, in which you're unable to record from the same cell for weeks and weeks. Okay, now it's a little better with the multi-unit electrodes, but it's still usually you are unable to record the same neuron for very, very prolonged times. So this is sort of a comparison of 50 different, so here it was 50 cells, 33 cells, and so on, at the different sessions. Okay, so this is before training, at the first 50 sessions, and so on and so forth. And what I want you to notice here, I mean, I'm not getting into the details, that there may be some differences, but if you look at later times, there's no great difference to what's happening in the pre-training. So what do we see? Okay, I didn't explain. The x-axis is time here, and this is just the firing rate. Okay, so this is what's called PSTH, a histogram depicting the firing rate, the average firing rate of these 50 neurons with the time of presentation. Okay, so you present the stimulus, I don't know, for a second, and you see that, okay, there's an abrupt response initially, then it sort of decays, but it stays high if it's at 100% coherence. If you're giving a stimulus at, I don't know, 6.4% of coherence, you get a lower response. Okay, that's what we expect. and that's in the preferred direction. But if you're sort of, what would you expect? You may expect that, you know, with, before training, let's just draw this. So to make the point, well, the neurons have a psychometric curve, right? Sorry, a tuning curve. They also have, you can look at the psychometric curve, but let's look at the tuning curve. So the tuning curve is, here you're going to have firing rate as a function of the direction of motion. So motion direction. And this would be, I don't know, between 0 and 360 degrees. And you're going to have, one neuron is going to look like this, another would look like this, and the third one would look like this, and so on and so forth. Okay? And with training, what could you expect? Maybe if there were training effects in MT, they'd be more sensitive to the direction of motion. So how would that be mapped in terms of the neurons? One possibility is that you're going to get that if this is initially, later it looks like this. Right? So it's more narrow, the tuning is more narrow, and there's a greater difference in the activity between the preferred direction and null direction. Okay? But as I'm showing you here in a different way, the neurons in MT do not change much. Okay? So it's not that their firing rate for the preferred direction increases. So compare the black line here to here, or this one to this one, you don't see much of a difference. Okay? Okay. So how can you start to understand this? Well, we can think about how is learning being performed at the level in the neurons. We can think about this as in terms of the decision that I was talking. Well, the decision is based on a comparison between a population of cells which is sort of, let's say, selective to upward motion, say this population, the blue ones here, and population 2, which are selective to the downward motion, right? And now, okay, so this is the tuning curve of the upward, these are the downward, and what we can think about, okay, so this is, so these neurons from population 1 and population 2 feed into neurons in the lateral intraparietal cortex, LIP neurons. And this is what these neurons do is just compare the activity of population 1 and population 2. If population 1 is higher than population 2, then motion was upward. If population 2 is higher than 1, motion was downward. Okay? And you can sort of think about this as, okay, this neuron would be selective, would get excitatory input from population 1 and inhibitory input from population 2. So if it's firing above its spontaneous activity, it must be due to population 1. And you're going to have a different neuron which has exactly the opposite sort of connectivity, meaning it gets excitatory input from population 2 and inhibitory from population 1, and you just compare the two. Okay? What do we know about these LIP neurons? Okay, so that's the basic idea of a simplified model for this. And what do we know about these LIP neurons? Well, first of all, just to give you sort of a geographical orienting, here's LIP here. So this is part of the parietal cortex. The monkey's eye would be here. That's the back of the brain, front of the brain, low and upper. So it's on the dorsal part, along the dorsal stream, parietal cortex. And LIP is here depicted in, it's actually in the sulcus itself. It's these dark blue and light blue colors which encode the LIP neurons. So they're recording from neurons around here in the intraparietal sulcus. And let's look at how these neurons respond. Okay? So unlike MT neurons, what I said was that they're sensitive to the impending action that the monkey will take, the eye movement. You can see this here. So now we can look at the activity of the neuron not only as a function of the presentation of the visual stimulus, but as a function 0 here corresponds to the onset of the saccade. So at some point, the monkey decides it's leftward or rightward, makes a saccade. So what you can see here is that there's a vigorous response if the monkey is going to make a saccade to the right direction, but there's very little response if the monkey is making a saccade to the left direction. So it has a motion field for rightward saccades, typically of a given amplitude here. Okay, so you place the target in the motion field, okay, in the motor field of that neuron. Okay, so it's saccade related. Now, if we look here, that's not the only thing that characterize this cell, because let's look here. So here is the case when motion is in the rightward direction. So you see, okay, here's the spontaneous firing of the cell, and you see that there's an elevated firing, right? Elevated firing if motion is in the rightward direction. Now, here, this depicts the coherence of the dots. So it's going from 50 on to 12 to 0% coherence. So basically 0% coherence, there's no net motion in one direction. So this here and this here are exactly the same. This depicts motion in the opposite direction, leftward direction. So you see here that there's much less firing than here, right? Surprisingly, also here, there's much less firing than here, okay? So let's think about this for a minute. How do we understand this? First of all, it seems to be motion selective, right? Because it fires more here than it fires when the action is in the opposite direction. But is it just motion? There's more to it, because here there's no net motion. It's just random motion. So how do you characterize this? It's a question. Think about this, and I'll wait for you to figure that out. You could give the wrong answer. Let's just sort of have a discussion, because you learn more if you I involve you. I think if I involve you in person. Okay. So this suggests that there's motion sensitivity, but this cannot be explained in terms of motion. So what is someone? Exactly. It reflects probably the decision, right? Because the monkey will make a decision eventually, because if you don't do anything, you're bound not to get any reward. If you make a decision, you're going to get reward in 50% of the cases. So you might as well make a decision. And indeed, it does make a decision. So this reflects the decision of the monkey to make movement in the preferred direction in terms of the saccade, saccade direction of the cell. Indeed, so. So it's, again, decision related. Okay, so, and you see that the firing starts well before the saccade. Why? Okay, so you see it's increasing, and it starts well before the saccade. Here, the vertical line corresponds to the saccade. How do we understand that? Because decision is formed about what am I going to do if the stimulus is very clear. All the dots are moving in one direction. I know I should make a saccade to the rightward direction. Okay, so it starts well before the saccade, and okay, this vertical line corresponds to the saccade, and it ends right after the saccade. Okay, and this is what you see here, basically. Okay, so I explained that. Notice that, okay, activity here at the time of the saccade is pretty much the same as you see here. It doesn't matter if the stimulus was at totally random or very, very clear. Why? Because you're committed to a specific saccade. So once you're going to make the saccade rightward, just before the saccade, you're committed to that saccade, and you get the same firing, same pattern of firing, irrespective if the stimulus was at 51% coherence or 0% coherence, which is the red line. They're just overlapping, completely overlapping. Here, if your saccade is going to be in the opposite direction, well, then the activity is very low. Okay, so the difference between this and this corresponds to which direction you're going to make the saccade. Okay. Another point to notice here, which I want to sort of focus, is what's going on here. So here, 0 is the time that the motion of the dots is on. Okay, so the dots are placed on the screen, and what do you see? Okay, well, initially there's not much firing. Why? I'm not sure, Matt.
You're calculating.
What do you mean calculating?
Like you're making your decision, so you're not.
Right. So there's a more trivial response, and that is the time that it takes for the cell to start responding is determined by how many synapses is it from the retina. Okay. So the visual stimulus. Okay. The visual stimulus has been set on here, but then you're activating first the retina, then LGN, then V1, then MT, and so on. So there's a number of synapses, quite a few synapses, before even the cell starts firing. So there's delay caused by that. And that's, okay, so that is irrespective of what the stimulus was, because it hasn't reached this area yet. Okay, the information hasn't reached this area. Now, you're right that, okay, so now what's happening at this stage here is you're accumulating, the cell's accumulating evidence. Okay, so the stronger the stimulus, the faster is the accumulation of evidence that the action is, that the movement is to, let's say, to the preferred direction, rightward in this case. And so if you're looking at 51%, you see that the slope is higher than, let's say, 6.4%, which is the green one here, okay? Now, what are the dashed lines? That's the accumulation of evidence that movement is in the opposite direction, the null direction of that cell. So there's a drop in firing. And you see that, again, it depends on the coherence, okay? So strong coherence is faster accumulation of evidence than the low coherence. But I want to draw your attention to these two lines. What are these? These are for 0% coherence. So they reflect the sort of the monkey's decision. Nothing in terms of the stimulus on the screen, because the stimulus is just completely random. But the monkey decides to commit, okay, to one action or the other, and that reflects it, okay? So if there's a signal, he's doing, he's sort of integrating information more efficiently to reach a decision earlier, but he does commit irrespective of what's happening in terms of the signal there, okay? So that's an interesting thing to look at. So how do we understand this? Well, again, I was talking about this neuron in LIP, which gets information from two populations of empty neurons, opposite populations. And the way you can think about it, okay, here's the stimulus. There's these two populations. And what you see here, the different lines are the activity you're going to get in these empty cells, okay? If you present a stimulus in the preferred direction, then you get an increase of firing. You present this in the null direction, you may get a decrease of firing. And, the lines here correspond to the coherence, so the darker ones are higher coherence. And what this LIP cell does is integrate information from these two populations of neurons. It's not just one cell. It's large populations which sort of converge into the, to LIP. Does an integration. And therefore, you'll see that as a function of time, the difference between these two populations is going to grow depending on the coherence, okay? So the higher the coherence, the speed at which this grows is higher, reflected in the slope here. Okay, so that's sort of a simplified model for how you can understand LIP activity as sort of an integrator of accumulator of information that comes from MT. And indeed, if you look at it this way, it's interesting because if you look at the early sessions compared to the late sessions, we'll compare these. Okay, so what do you see? That's exactly, it's similar to what I've seen here. It's just sort of the grand average of the neurons here. So compare this to the late sessions, you'll see how this, first of all, the slope is much faster, okay, meaning that you're integrating information more efficiently, okay, in the later sessions than the early sessions here. That's corresponding to the fact that this sort of the slope here is much faster than here, okay? And that is clear. So the empty cells have not changed their firing. What you're doing here is getting a better integration of the information. So the changes in LIP, So the changes in LIP reflect the improvement of behavioral sensitivity to weak motion signals with training. Okay, so it's especially so with the weak motion signals that initially, okay, you hardly can tell them, and then they become much more clear with training. So the monkey now is able to discriminate between two motions in a sort of preferred and null direction, upward versus downward, even if at low coherence levels, which initially he was not able to do. Okay. So how do we understand this? Any idea? Okay, so remember that the cells here, an LIP cells gets input from these two populations. How can we think about this? And it gets better. Okay, this integrator gets better, more sensitive to the motion signals. Although the motion signals in empty, okay, they're not becoming better. They're not, the empty cells themselves are not getting more sensitive. The LIP cells getting more sensitive. How can we understand that? Well, we can understand this in terms of, remember that I talked about these neurons with a tuning curve here. So let's think about one population here which is tuned one direction, and another population which is tuned to another direction. Well, what you want to do is pull this population here. Let's say they would be the positive population here, okay, right? So the positive, these P cells here. Now, you want to get a better estimation of what the stimulus is. How are you going to get a better estimation of what the direction of the motion was? Well, so I drew here these, 4 tuning curves with some jitter in their preferred direction. But the most important thing, so that's one aspect, but the point that I want to emphasize is the fact that, okay, they have different tuning in terms of what is their peak. Another point here is what is their standard deviation. So there's a sort of a tuning curve here, and the bar here corresponds to the standard deviation, which means what? You're presenting the same stimulus over and over again. As I said, the cell is somewhat noisy. It wouldn't fire exactly the same number of spikes if you repeat the same stimulus, okay? So the greater this bar means that it's more noisy, okay? So what you want to estimate basically is the signal to noise of each neuron. How good is this neuron in saying, okay, from its firing, what was the stimulus, okay? So the higher the activity, okay, the difference between the preferred and the null direction is bigger, okay? The higher this tuning curve is, the maximum, the better it is. But another aspect is, what is this arrow bar here corresponding to the noise in the response on individual trials. And the smaller that is, the better it is. Now, as I said, when I was talking about MT, this does not change in the neurons, in MT, okay? So it's not that let's put it this way. If the neurons in MT were becoming more sensitive, what would you expect? 2 options. I was talking about one, and then, okay. I was talking about one. One is let's take this neuron in MT. The blue corresponds to the tuning curve initially, and the black here corresponds to, let's draw it again just to make it clear which one I'm talking about, at the later stage. So there's an increase in the maximum firing, okay, in the preferred direction. That's one option. Okay, for an improvement of signal to noise. What is another? That it doesn't increase, but you can think about, okay, let's draw this one. You can think about the tuning curve. There is a standard deviation here in terms of the noise expected on individual trials when you repeat the same stimulus. So that may decrease, okay? If this initially is like that and later it's like that, it means that the noise has decreased. So the signal to noise has improved. So these are 2 ways that you can improve the signal to noise of individual neurons. None of them happen in MT, okay? So in MT, there's no change in that. Well, but the monkey does improve. So how can that be? We said, okay, it's improving because something's happening at the level of the accumulation of evidence in these LIP neurons. What is happening? What is happening is that they become more sensitive. Remember this? So these neurons are becoming more sensitive to weak signals. Well, how does that happen if the empty neurons do not change? What's happening is that you assign weights. So you can think about this neuron that it pulls information from these preferred direction neurons here. And here's, so neuron 1, 2, 3, and 4. And these are corresponding, the triangles here correspond to the weight of these neurons on this LIP neuron. Okay, well, some neurons are better than the others in the sense that they have a better signal to noise ratio. Okay, which is the best one from what I drew here? Number 2 here, right? Because you can see that, okay, has the highest firing rate, and the arrow bar here is, I don't know if it's the smallest, but it's pretty much the same as the others. So it would have the best signal to noise ratio. Okay, but number 3 here is not ideal in the sense that it has a great arrow bar here, meaning that there's a lot of noise in its response. So one way you can think about it is, okay, let's give a higher weight to number 2 at the expense of lower weight to number 3 in the decision. Okay? And that would, so you're now changing the weights given to these input empty neurons onto these LIP neurons such that it would be more sensitive. So it's one way, we don't have proof for this, but it's one way to understand how this results in better sensitivity of these LIP neurons, which would lead to better performance of the monkey. Okay? So this was a sort of a point to the way we're starting to think about this. Currently, I think, as you will hear later, there are techniques that are now sort of being used to try this, to address this directly. This is sort of work, and I think the better choice for such studies is using rats rather than monkeys. It's very difficult to sort of assess now here the synaptic weights that are assigned to individual cells here in this condition. But okay, I just wanted to give you sort of an idea of how we think about these problems. Okay, and let's move on from here. Okay, so I've just finished my presentation for today, and I'll start the presentation for the next session, which is sort of going to be an intro, half an hour, quarter of an hour intro, so quarter of an hour now and half an hour in the next, on Sunday, sort of presenting the stuff before the students are going to give their sort of seminar or their short lectures about, some more advanced aspects. So, to jump into this, we talked a little about motion processing pathway from primary visual cortex to area MT, and from there to parietal cortex to area LIP. So that's sort of along what's called the dorsal stream, which is typically thought about as sort of the stream which is involved with vision for action, for making a specific action. In this case, it was a classical dorsal stream task in the sense that basically the monkey, based on the stimulus, had to choose an action, leftward versus rightward saccade. Okay? Now I want to sort of focus a bit and give you some introduction about the other pathway leading from the primary visual cortex, which is going to the ventral stream. So this is up dorsal, down to along the ventral stream, and ending in infratemporal cortex. Okay, and this pathway is typically thought of as the pathway leading to object recognition, following the work of Goodale and Milner. So you've heard about this. You know something about the two pathways. Okay, how was this? Okay, so if you've heard about this, let me raise a question. How do we know this? Well, first of all, exactly. So the classic work of Goodale and Milner were using humans with specific lesions that involved either the parietal cortex or the infratemporal cortex, okay, in which, so the classical one is that if you have a lesion in the infratemporal cortex, you are able to grasp objects, okay, but you're unable to identify what they are, okay? And the classical example is that if you're given a sort of a letter and you have to put it into the post box, and you change the orientation, okay? So you change the orientation of the slit of the post box, okay? These people that have a parietal lesion are unable to do this, but people that have lesions of the infratemporal cortex have no trouble in that. But so that's vision for action, okay? But if you're asked to identify the orientation of this sort of cell phone that I'm holding, then people that have a lesion in the temporal lobe have great trouble in that, and they have trouble also in sort of naming objects. Okay, so their object recognition is failed, while they can still function in terms of vision for action, grasping the objects correctly, although they're unable to name it. Okay, so there's this distinction between the two. Okay, and sort of just to give you sort of a feel for what are we talking about. So I was talking a bit about the retinal ganglion cells and the LGN. Remember, we talked about magno and parvo pathways. This is sort of the connectivity, partial list of the connectivity between various cortical regions, starting from along the visual pathway, starting from the retina. Okay, so it's quite tricky. We talked a bit about and just to make it more tricky, different anatomists use different names for it. But we talked a bit about MT, and then we talked a bit about LIP, and we talked a bit about the sort of functional organization of V1. Now I'm going to be talking about the ventral pathway, which is this one here, leading from V1 to V4, V3, V4, and then going to infratemporal cortex. Okay? A better way to look at it is from here, just to get an idea of the anatomy. I mentioned this to you. So the colored areas here are the visual areas, and you see the information from the retina to moving on to the LGN, V1. This is sort of the atlas, so the 2D sheet here of cortex, which you see here. Okay, here's the eye, just in a monkey brain. So you see just to get an idea of how big the brain is with respect to the eye. Okay, and these are the visual areas here colored, and this sort of flattened map of this. So we're talking about information now going from V1 and sort of leading to this temporal area here in infratemporal cortex. Okay. And just to get an idea in terms of the timing, so I'm talking, this is the anatomy. Now, if you look at it's related to a point I made before. If you look at when do the cells start firing, okay? You give a stimulus at time 0, okay? So the x-axis is the time from stimulus onset. And the y-axis is the percent of neurons that are active in a given region. Well, who are the first ones? In the LGN, that's not surprising. Okay, they haven't recorded from the retina. The LGN is the first relay station, so that's the first ones. And notice there's a difference between the magno and the parvo LGN. Remember, I mentioned about the two pathways. Well, the magno is the one which is responsible for motion, okay, flicker motion, much faster than the parvo. Next is V1. Okay, so you see that it's increasing. It's sort of a cumulative Gaussian, okay, because it typically, if you look at the 50% point, that's the time at which the cells are now active, okay? And some of them are more delayed than the others. So some start early, some start late, but, if you took this and this is the integral of a Gaussian, which is, I don't know, in the parvo, it would be maybe 45 milliseconds before the average cell starts to fire. And here's V1. And a few things to notice. First of all, so it's related to what I talked before. The activity in the motion pathway starts well before the activity in the ventral stream. Okay, so V2, V4, that's along the ventral stream. So that starts at about 100 milliseconds in V4, or I don't know, 80 or 90 milliseconds in V2, but it starts much earlier in the motion pathway. Okay, probably because the activity in the magno LGN starts earlier, and that feeds into these ones. Another thing to notice, which I didn't talk about, is this area here, FEF. That's the frontal eye fields, which is another region, just like I was talking about LIP. Frontal eye fields is a similar region, which is responsible for saccadic eye movements. Okay, you may have heard from Mati Yoshua, because he's working on this, on saccadic eye movements and smooth pursuit, and areas here are active in that case. And notice how early it is. Okay, they're active, so there's a sort of a pathway passing V1, or V1, V2. Sorry, V1, it doesn't pass V1, but it typically passes V2, certainly V2 and the others, to lead to the frontal eye field. I'm not sure if it's okay. Here's the frontal eye field. You see that it has direct pathways. Okay, going from. It's not listed here. It says, it sort of points out that it's through V2, but it's earlier than V2. So it certainly does not pass through V2. That's just to make the point that you get something about which areas are activated first, which are later, okay? So that's an interesting point. And now, if I'm focusing on the ventral pathway, I want to give you some idea. Okay, so we talked about information from the retinal LGN getting to V1, and then moving on to the ventral stream here. And so you see here, first of all, the latency of response, which I've just shown you. And here you see how many neurons, how big is the area, and how many neurons are involved in each of these areas. So you see that, okay, just to get an idea. There's about 1 million retinal ganglion cells which feed into the LGN, okay? And that's about the same size. When you get into V1, there's a great divergence. So there's much more cells in V1 than in the retina. So really, the the limit for the visual acuity is in the optic tract, okay? The pathway originating from the retina and going to the LGN, okay? And that is, you can think about how many pixels are encoded, okay? So each each retinal ganglion cells is responsible for a specific visual field, and the limit in terms of acuity is already at the level of the retina, because there's much more neurons in V1 than there's in the retina, okay? So that is really a great bottleneck for information process, visual information processing, because the number of pixels that you can possibly have. Okay, and then you have the information feeding into V2, V4, and so on and so forth, and this sort of corresponds to where is it in terms of the anatomy. So you see that this is taking longer and longer time, and you get an idea of how big these areas are. So, you know, the area is biggest in terms of the scale of the area devoted to vision. V1 is by and large the biggest area with like 200 million, 190 million neurons, while these are much smaller. Okay? But there's something happening in these areas. Now you can say, okay, why do you need all these visual areas? Okay, so there's a map in each of them, right? We know that there's a sort of representation of each of them. Well, any idea why would you need, 30 areas? Why do we need multiple visual areas? The question. Well, because you'd think, and so the example I've given you for MT is they each specialize in a different visual function. Okay, so for instance, MT neurons seem to be specialized for understanding motion, okay, for deciphering motion direction. By the way, it's not that they're only sensitive to motion, they're also sensitive to disparity, where is this depth in the world, which you can get into. But generally, you can think, okay, that's one. First of all, we don't know the answer. But one reasonable assumption is that there's a specialization, okay? That each area is specialized for a different visual function. Okay. And this is just to portray this in a different way. So if you look at neurons in V1, which we talked about a bit, they're orientation tuned and they have certain receptor fields. As you're moving along the hierarchy from V1 to the infratemporal cortex, receptor fields become bigger. And you can see here that the receptor field size, if in V1 they're of the order of a degree, depending on the eccentricity, but they'd be a fraction of a degree to maybe 1.5 degrees. As you're moving to higher and higher order areas, receptor fields become bigger. So that's one thing. They become bigger. Their latency is longer because they're more far away from the retina in terms of synapses. But another important feature is, which I've just mentioned, is that they become more sophisticated. If initially the neurons in V1 are tuned to orientation, they may be selective to specific spatial frequency, as we talked about, these sort of Gabors that we talked about, Gabor functions and filters that we talked about. As you're moving on to V2 and V4, there's a sort of some new characteristics of the cells which do not characterize V1 cells. So first of all, they may be tuned to more sophisticated stimuli in terms of shape. They're also tuned to, some of them would be tuned to, in this case, this is what's called a subjective contour. And you'd have a cell with a receptor field here, which is sensitive to this orientation here. But if you think about it, okay, so you see these Pac-Mans which draw a rectangle here oriented. We all see this. But in terms, if you were to pass a light detector along this line here, of course you wouldn't see anything, okay? We're sensitive to that, although there's no difference in light along this pathway. We are sensitive because we are taking into account that these lines, we connect them. Although they're not connected, we connect them. And we build a sort of a rectangle out of something which is non-existent there. So we call this subjective contours. And subjective contours can be found in higher order areas in like V2, rarely found in V1. And as you move, you get to a situation where you go to temporal cortex. Suddenly you see neurons which are firing to specific stimuli. We'll get to that in a minute. I think my time's over and I lost my voice, so I'll probably end up here. Just to mention that this is again showing sort of graph showing which areas are active early and which are later. Okay, so from 40 milliseconds to 50 to 65 after stimulus onset, you see, okay, initially V1 and MT, then you get sort of this frontal eye fields that I talked about that are related to eye movements, and 7A parietal, again moving area related to eye movements. MT and MST and FST are also motion related, and you see that with time you get further and further activation of also the ventral stream, and not so initially the dorsal stream more than the ventral stream. And I'll get to that. Time's up, and you want to have a break, so do I. And if there was an urgent question, someone asked something, and I didn't have time. If not, we'll start. We'll have about a half an hour that I'll in the next lesson where I'll be giving an intro, and then we'll hear the students. Okay? Let's see. Bye-bye. ברור שאי אפשר להציג את כל הפיצ'רים, אנחנו לא יודעים מה הם, אוקיי? נדבר על זה בתחילת שיעור הבא. באמת שאלה מצוינת, אוקיי? כאילו, מה הפיצ'ר ספייס אתה רוצה להשתמש? שאלה ממש מצוינת. כן, כדאי שתבואו לדבר איתי. אתה ודיינו, נכון? אוקיי. אז אולי... כן, כן.
המון דיטייל.
לא, אז אני רוצה לדבר על כמה דגשים. אולי נראה את זה לי תכף. טוב עכשיו, אתה יכול לומדים עכשיו או שזה...
אני לא.
אז בואו ניגש, יש לכם את המאמר, וזה נבוא ונסתכל טוב, ואני אגיד לכם עכשיו עוד נגיד, תנו לי רבע שעה להתאושש, וב-11 גם נפרד. בסדר? אם קבענו, אני רשום לי ביום אחד, לא נפרתי. 100%, כן, לא יודע.
שלישי רביעי וחמישי, את לא יכולה, שני שלישי ורביעי. אין לך טכנית את הזמן, אנחנו עד 6 לדעתי, אגב, לא לצאת פעם ב4.
כן.
שזה כן.
כן, גם לדעתי.
יש לנו מלא וריאנטים.
ראית כבר?
אתה רואה?
אתה לא מלפור, זה דווקא בקטני חושבת. זה לא עושה את זה? לא, לא, אני לא עושה נכון.
תגיד, אתמול
אקדמי, אני מרגישה שהם חיים מרוב אקדמי, כן?
רק על זה?
שהם חיים מרוב אקדמי.
לא, זה שטויות כאלה.
מה לא אקדמי? בגלל כל היום באקדמיה.
הרי כל מאמר נגמר בשאלות להמשך, נכון?
לא, זה ממש ברוב, בלי שאלות להמשך ועם דיון ממש ברוב. אז אני יכול לעשות להגיד להם...
בטוח שהם לא ענו על כל השאלות.
מה משמעות החיים של הלימון? אני חושב על זה.
זה מקום טוב.
עדויות קוגניטיביות משמעות זה.
תגיד למוח מילים. כבר יש לך כזה תגובה, זה מקום תחום.
לא, אני טוב למצוא כבר מוגברת 42. אצלי ואם חוזר בזמן במאמר זה יש בתחושה עם זה כמובן.
תמיד זה אומר במאמר.
במקור אפשר להגיד, זה FBM.
נכון, זה FBM.
וואי.
בדיוק, כמה אפשר לצפות את הדבר הזה, והצלחת. תגיד לי, בקורס של המאה ה-18, מי צודק? אני? כן. סתם, 18.
מי צודק? אני או יהודה?
שמה? באיזה הקשר?
שמות חיים.
טוב, בניהול המשמעות חיים זה לא יודע מה.
טוב, בקיצור,
מה צריך לעשות?
זה בדיוק מה שאמרתי.
אוקיי, כל אחד צריך לעשות בשביל עצמו ויש אחד פוזיטיב.
אחד בשביל עצמו ואחד בשביל כולם.
נכון.
הדיון הוא מצד הלעיתים. למה הוא כותב לי כל הזמן?